All right, so now we got it recorded, although I think everybody's on today. But let's go into Khan Academy, get logged in, and see if you see there should be like, I want to know how many assignments you see. So the first one to get logged in and see how many assignments I have for you that are due on September 30th is going to be the winner. And it is possible that Hannah and Kylie can both win since they're sharing a screen. And Section 1.7 evens are going to be due tomorrow. So the assigned ones, not all of them, just the assigned ones, by class time. And then what I'd like to do, if I have everybody's homeworks through 1.7 by tomorrow class time, I will share my keys with you as long as you don't share my keys with anybody else. And just to make sure that we're all on the same page for the 50-point quiz on Thursday. 155. Well, that would be a good thing because I had assigned, I thought 103, and then today it looked like nothing was assigned. So if it says 155, that's awesome. Did anybody else see 155? What that means is I reassigned the same thing today then, which I didn't want to do. Anyway, I want everything up to, I see a few people actually got on there. Let me. Isaac, I see that you had done some stuff. Were there assignments already on there? Were there like 100 assignments?
Yeah, there were a bunch of assignments.
All right, so the ones that I assigned today, you do not have to do those again. And you don't have to do all 103 assignments. You have to do the ones that have exercises. If you want to watch the video, the introduction or those types of things, you can. That's there for you as well. And so I do want those done by Thursday. So I'll try and be a little more specific. We'll kind of go through them. I'll share my screen with you, and then we'll see that today. In fact, why don't we just, I might as well start out with that since you're all in Khan right now. So let me share my screen.
Yeah, everything's listed twice here.
Yeah, so don't do it twice. Do the first ones listed, not the second ones. That drives me crazy.
Okay.
Not sure why it was showing it that way to me today. Do I want to switch to tablet mode? Yeah, I guess. All right, can you see Khan Academy on my screen, on your screen?
Yeah.
Okay. So anyway, when we get in there, I'm just going to go through this again. I'm going to click on limits and continuity. I think. Anyway, so the things that when you have a video like introduction on limits, once again, we're going through that in class. If you want some additional stuff, you can do that. If you want to read articles, things like that, you can. But the reality is, so these first two here, these are optional assignments. I'm not expecting that you have to do that, but if you want to, you can. And then when we get into things like the limits intro, can you see we did this before, right? And so then you go and answer the questions there, right? And so I do want you to do that. They have like so many exercises that you're supposed to do there. I'm in the student view there. Anyway, so make sure you do that. And so there's really There's one there. So anything that says exercises, there's two there, estimating limit values from graphs, one-sided limits from graphs right here. Can you see it underlined when I'm touching it too? Can you see my hand moving when I'm using my pencil to make a hand? I can't, I gotta go back. I'm not getting alerted. Let's see. Yes. Okay. Gotta go back to it. All right. Perfect. So anyway, anything with exercises do, and then as you work down, then you have a quiz. So I'll expect that you do the quiz too. And then let's just keep going down. When we get into limits and continuity, I am not doing continuity yet. So right before this, up to the squeeze theorem is really what we want to do. So I'm not making you do the third quiz. So try to get as much or some of this stuff done as much as you can by tomorrow as well. But I do want you to be able to work on it. So even though it said 103 assignments, the ones that have exercises are not nearly that much. I'll see if I can't figure that out. And then I'm going to delete, hopefully, the ones that are duplicate if I can see what I'm doing there. All right. Anyway, so now let me go back to, what is this? This must be my, yeah, that's the wrong course. All right. So I'm going to go back here. Let me go into the whiteboard. Nobody has any questions, obviously. First, I guess Jordan, you and I are going to have to figure out what we're doing since you can't actually be physically there when we're taking that quiz. So I'm going to have to figure out what we're doing there for you. Anyway, so now hopefully you see the whiteboard. Share the blank whiteboard. I'm sharing that. All right. And let's just a couple of things real quick. I finished up a couple of things. One was number 19. We did this in class, and then I sent something on WhatsApp. But what we had was the limit as x approaches 3 from the right of the square root of x squared minus 9 all over x minus 3. If you plugged in using the limit theorems, we end up getting 0 over 0, right? And 0 over 0 is an indeterminate form, so then we needed to either factor underneath the square root and then simplify, or multiply top and bottom by the square root. That was another way to work. But a lot of times this ends up being a whole, but in this case, it could be an asymptote. So we're not defined there. So in this case, it ended up being an asymptote because this limit, when we worked it out, actually existed and equaled positive infinity when we did that. So that was from last time. So what happened there is we approached a vertical asymptote. So as x approached 3 from the right, so we'll look at that. As x approached 3 from the right, my graph actually explodes upward there. And so it was not a hole. In this case, it was actually an asymptote for the right-handed limit there. So I did want to note that. So 0 over 0, a lot of times we were used to it being a hole, but that was an example, specific example where it was actually an asymptote. And then I did number 21, and I sent out a picture of it, but just to do this together and kind of talk through it together, we have the limit as x approaches 0 from the right of 1 over x and then minus 1 over x squared. Once again, if we just plug this in and say limit of the difference is the difference of the limits, and limit of the quotient of the limits for each one, what we're going to end up getting here is, since x is approaching 0 from the right, this one ends up being positive infinity, and this one ends up being positive infinity, and what we have is infinity minus infinity. And the question is, what does that equal? Well, we don't know, because we don't know which infinity is bigger. Does this infinity, Is that bigger than this infinity? Are they exactly the same? Are they approaching it at the exact same pace? Or is the second infinity approaching a lot quicker? The first infinity could be approaching twice as fast as the second one. So this is one of those indeterminate forms here that we need to do something else. So one of the things that we could do is manipulate, since we have an indeterminate form. By manipulating, what I could do, one thing I could do is I could get a common denominator, and I could multiply top and bottom of the first one times x. And so then I'm going to get the limit as x approaches 0 from the right of this would end up being x over x squared minus 1 over x squared, and then I'll have x minus 1 all over x squared. And if I do that, now I can go ahead and plug in limit of the quotient is the quotient of the limit. And then, of course, limit of the difference is the difference of the limit. Limit of the exponent is the exponent of the limit. We have that. But anyway, just plugging in, since they're polynomials, if I plug in, it doesn't matter that 0 approaches in a positive way on top, because really I can just plug in 0 here for x, and I'll get minus 1 on top. Now, on the bottom, it does matter, because when I plug in a 0 for x, I got to know what kind of 0 it is. However, I'm going to have quantity squared, which even if it was approaching 0 from the left, I would actually get a positive 0 in the denominator, because I would square out the minus sign as those numbers get tinier towards 0 in either direction. But anyway, now I have a fixed negative number divided by something that's approaching 0 in a positive way. This explodes to negative infinity then. So it explodes to infinity, but it's actually negative infinity is what it approaches. So really, coming back here, the second infinity approaches infinity a lot quicker than the first one did. So basically that kind of overtakes it. So this is one of those indeterminate forms that we needed more information, and we end up with a vertical asymptote where, once again, if I was going to graph this now and I'm approaching 0 from the right, my graph is approaching negative infinity down here. So it explodes downward as x approaches 0 from the right. So as my x's come in here. So hopefully that makes sense. That was number 21. And then I did mention some other indeterminate forms. So this kind of goes back to first day of class. We know that 0 over 0 is indeterminate. So these are indeterminate. We need more information. We don't know what the values are. Indeterminate forms. 0 divided by 0 is indeterminate. 0 to the 0 power is also indeterminate. Normally, if you say x to the 0 power, well, that's going to equal 1. Anything to the 0 power is 1, but that's only true if x doesn't equal to 0. So if I have pi to the 0 power, that equals 1. Okay. If I have 5 to the 0 power, that equals 1, right? But if I have 0 to the 0 power, that's actually indeterminate. So is 0 divided by 0. And then we can also say that some of the other indeterminate forms are, we already said, infinity minus infinity. That's indeterminate. We could have minus infinity plus positive infinity. That's indeterminate because we don't know which one's bigger. We also have infinity divided by infinity is indeterminate because I don't know which one is bigger. And then I could actually have plus or minus infinity on top. I could have plus or minus infinity on the bottom. So we actually have 4 different indeterminate forms there. Because once again, which one is the numerator approaching infinity faster? Is the denominator approaching it faster? Same pace, or what's going on? So those are indeterminate as well. But we do need to note a couple of things. And once again, I did send a picture out on this. But if I have infinity plus infinity, if I go to the right without bound, and then I add going to the right without bound, that's going to actually go to the right without bound even more so. So that's going to, infinity plus infinity is positive infinity. We could also say minus infinity is going to the left without bound. Really, this is equivalent to minus infinity plus a negative infinity, right? If you add the opposite, well, that equals negfinity, right? So minus infinity is minus infinity. And I could actually multiply things that are approaching infinity together. So infinity times infinity is infinity. I could also have infinity times negative infinity is negative infinity. And then, of course, if I had minus infinity times minus infinity, that's going to equal positive infinity, right? And similar there, I could have the minus on the other side too. So I could have minus infinity times positive infinity, and that's going to equal minus infinity. So I have those, and we're fine on that. But just some of the indeterminate forms, adding infinities together of opposite sign is indeterminate, or dividing them is going to be indeterminate as well. Okay, so I think unless you have a specific question on anything from section 1.7, that I am done with my presentation of everything that you're going to be quizzed on. One of the guarantees on your quiz is you will have an epsilon delta proof for a limit, probably for a line, because I said you have to know the lines, right? You have to know your lines. It's like if you're in a play or doing a cheer. So anyway, all right. What do we got? No other questions from 1.7? Or what's due? So basically 1.7 evens that I assigned are due tomorrow. I'll make sure you get a key before we take that. Oh, I got a question. What is the homecoming schedule? Which days are messed up?
That's a good question. I don't think anyone knows.
Jack, you're at home, right? Do you know which days are messed? It doesn't. I guess it doesn't matter to you, but we're all gonna have to know which ones are messed up. Friday's messed up, right?
Yeah, Friday is. I know I'm at
They
school.
usually have a parade. Is there an early out? I don't even know.
Nobody knows, not even the principal.
So we got to be a little cautious here. By the way, and then not only homecoming, but then we also have conferences. If your parents want to talk to me, they're going to have to call me because I'm not going. But I'm not a Kemper employee. Okay. Conferences, but the day is messed up. So note that we normally meet, you're getting out of school early, but we normally meet 1:15 to 2. I don't know if you have practices and stuff like that, so you need to let me know if you're available or unavailable for those. Because once again, my schedule doesn't change with conferences, but I know you're not in the building after 1 o'clock, and I think that isn't that Monday, Thursday next week. So I don't know. This is just be glad that we didn't have to do this at 7 a.m. I guess. Although I'm thinking that'd be a lot easier. Anybody know, can anybody, like, I guess somebody, if you find out what the schedule is, I'll try and find out too, but we're going to need to know what days are messed up. Thursday's okay, right? Can somebody give me a yes that is a normal day?
Wednesday.
I think Thursday's good.
No, you don't know. Are you guys still there? Are you awake? Looks like you're there.
Yeah, we're all here.
Luke, is Thursday a normal day?
I don't think so.
Maybe?
I think it's a
no,
2 hour early out, isn't it?
It's either gonna be Wednesday or
not this week. We're talking about this week, Carter.
Oh,
This
yeah.
week.
next week.
No, this week. This week should
Thursday should be
Hello, can you guys hear me?
it should be
It's either
normal.
gonna be Wednesday's a math day or Friday's a math and
Luke,
yeah. And then
Yeah.
the parade is like
chat me or text me if Thursday's a normal day for schedule for Kemper. Did you guys lose your okay, thank you, Luke. Like, you guys doing, I don't know what you're doing there. I might have to have you show me your screen. All right. Here we go. Let's go into section 1.10. So I'm going to go into continuity because nobody's given me any questions. So let's look at continuity. So we got 3 more sections in chapter 1 after your half test. 1.8, 1.9, 1.10. Everything else then is I have instruction videos too, so that'll be even better. So we'll move on. But anyway, section 1.8 is continuity. And so what's the difference between continuity and limits? Well, if you remember with a limit, what were we doing? We were, the limit, we were getting as close as we wanted. Limit as x approaches a of f of x. We were getting as close as we wanted to that point, x equals a from both sides, but we never touched the point. And then we had what that limit was, that height, right, is what it approached. But we never touched a. So we approached it from the right and we approached it from the left, but we never actually touched a. Well, continuity is different. Continuity, we actually are going to touch a. So we're actually going to hit that point, and we want, so to be continuous, we're going to define that. Definition. So f is going to be a function, and we're going to say that f is continuous at the point x equals a. So it's continuous at the point x equals a if and only if 3 things happen. Okay. The first bullet point is f of a has to exist. So in other words, we need to be defined there. Okay. So when you plug in a, x equals a into the function, you actually get an output for a height. And then number 2, the limit as x approaches a from both sides of f of x also must exist. So we're going to be able to find that limit L. And then the third thing for it to be continuous is that these 2 things are equal. So 1 equals 2. So not only does f of a exist and the limit exist as you approach a from both sides, but those 2 things are equal. Okay, so let's look at, well, let's note this then. Let's make a note. So we're going to say f is not continuous, or what could be said discontinuous. So discontinuous at x equals a if at least one of these fails. So one of these bullet points. If one of these bullet points fails, it's going to be discontinuous. So we're going to look at pictures. So here's the 3 bullet points. If at least one of those is not the case, then f can't be continuous there. And if it's not continuous there, we can say it's discontinuous at that point. So this is continuity at a point. So let's look at a couple of picture examples here. We're going to look at, first one, we're going to look at, here's my function. There's a. This is f of x here. Is f continuous at x equals a? Somebody want to just chat in? Isaac says no. Isaac's correct. So f is not continuous at x equals a. And why? Because which one fails? Number 1 fails because f of a does not exist, right? So f evaluated at a does not exist. Okay, good. Let's look at another example. Let's look at this one. So here's a. Here's the blue sketchy curve is f of x. What about this one? Is this one continuous? Somebody besides Isaac. Isaac and Luke are done for now. Somebody else has to chime in. Is that continuous at x equals a? Jordan, good. It's not. F is not continuous at x equals a. Why is that? Which one fails? Number 2, right? 2 fails. Why? Because the limit as x approaches a from both sides of f of x does not exist. So in this case, 1 doesn't fail because f of a actually does exist. It's where that darkened blue dot is, whatever height that is, right? However, the left-handed and right-handed limit are not the same, so 2 fails. By the way, 3 also fails because 2 fails. 3 also fails in the top one because number 1 fails. But as soon as we find one that fails, it's not continuous. Once again, we could also say f is discontinuous at x equals a. So let's look at another example here. Once again, we're just going to draw ones different scenarios of what's going on, what could be happening. There's your function, and there's your height f of a. So here's a f of a. So I am defined there. The question is this continuous at x equals a? Somebody besides Luke, Isaac, or Jordan? You guys awake? Like, what, are you taking a shower at home, or are you sleeping on your desk? What's going on? Is that continuous at x equals a?
No, because two.
Well,
No.
f of a exists, right? So that's not a problem. The limit as x approaches from both sides exists and equals L. However, thank you, John. But f is not continuous because which one fails? Number 3 at x equals a, right? Thank you, Hannah and Kylie. So number 3 fails. So f of x or f of a exists. The limit as x approaches a of f of x also exists and equals L. However, they're not equal in this case. So 3 fails. All right, so that's good. So, and what does it mean to be continuous? Well, let's look at that. Well, I'm going to do one more before I do that. Let's look at one more example. There's f of x right here. Here's a. There's f of a. Is this continuous at x equals a? No, correct. Why? One doesn't fail. It's not 1 because f of a actually exists in this case. Sorry, maybe that looked like an open dot. So f of a exists. Okay, so 2 and 3 fail. So tails. Number 2 fails. And why is that? So remember, number 2 is the limit as x approaches a from both sides of f of x must exist. And this does not exist. And the reason is because the left-handed limit does not exist, right? So that's kind of abbreviation. The left-handed limit, LHL, left-handed limit, does not exist. So as I approach a from the left, f doesn't even exist. So basically, I need to be, for continuity at a point, what we're going to need is we're going to need to be defined not only on some open interval containing a, but in this case, we're going to be defined at a itself. So really what we're going to need for continuity, our picture is going to end up looking like this. Here's our function f of x. This is an example. So I'm going to need to be defined on some open interval containing a, including x equals a, because what happens is f of a must exist, and that also must equal the limit as x approaches a from both sides. So I got to be able to approach A from both sides. I also need an output that's exactly the same. So basically I have to, if I have a hole, I have to fill the hole. We can't have, for continuity, we're going to want, so for continuity at X equals A, we're going to need to make sure that we have no holes, no rips or tears, and no jumps, which could be like a tear. So I don't care how you think of that. These are kind of the same things here. No holes, so no asymptote. And we also, as in that last example, no stops. We can't just get to the point and stop. So we have to be able to draw the graph without lifting your pen, right? So you need to draw the graph through the point without lifting the pen. My writing is bad, but it's even worse on this pad. Draw a graph without lifting your pen. Right? So that's, we want to draw through that. It's got to be a function. If it's not a function, we're not even talking about continuity. Oh, it looks like it's time to go. So that's just an intro into continuity. So keep working on con and then just the assignments and 1-7. We'll go over that tomorrow and get ready for your half test. Later. Happy homecoming week.